I'm Brennan Ashton.
Technology. I'm Dave Knight. And what we decided to do here was get a quick snapshot of what we could possibly do with any building on WPI campus. We found that Atwater was probably a good building to do this with because it has many different types of facilities. And go ahead, what do we do?
So we looked at the computer use, which is fairly significant in the building. A lot of computers are left on. A few different types of lighting advancements that we've done, switching to LED lighting, or even a phenomenon called daylight dimming. We looked at in particular.
We also looked at the heating in the building, and what we found was that the heat is kept at a very high level even overnight with no one in the building, so that is another way to cut down on energy.
Overall, our changes to the building will pay for themselves within 5 years and save over $200,000 in the comparable amount of energy to the WPI community.
I'm Ryan and together we looked at building library energy efficiency, how we could improve the energy efficiency of the library that we're currently standing in right now. So for our project, the library was built in 1967 and it's 42 years old. So we looked at different ways that we could improve the whole energy of the system. And we looked at 4 different aspects of the library. The first involving adding photovoltaics onto the roof, the second involving adding insulation to the windows, and the third the walls. And as well, we looked at the technology within the library, from the TVs to computers, and pretty much reducing the energy loss.
What did you learn?
So by calculating, with all of these systems, we calculated the paybacks. For the photovoltaics, we came out to about 17 years it would cost to pay back for purchasing the photovoltaics. For the windows, adding insulation, we looked at 2 different insulation types, and thermal window shades, and that would be about 45 years payback price for those, and the walls would be approximately about 3 years with the added insulation. And basically for the technology, we looked at ways to reduce the overall use of the technology. Basically from switching from like normal lockdown mode to standby, and that would allow the computers to use less energy and therefore save the library money.
Yeah, we kind of looked at trends to way to improve the library without being intrusive and trying to look at ways like the technology is just really just spreading awareness.
Hi, I'm Kevin Hudson. Hi, I'm Charles. And this is our Great Problem Seminar, Power the World project, entitled Distributed Power Plant Options in Urban Design. What we did was approach the issue from 2 different sides, from a social standpoint and a technological standpoint, in terms of providing power from on a more efficient, reliable, and environmentally friendly basis.
And we did 2 surveys. The first survey is on campus in WPI, and we asked them about their opinions about our project. And the second survey we did in China, which is 3-hour survey, questionnaires in China, like universities in China, and asked them about their opinions.
We also came up with some policy recommendations, which is about the capacity building and the direct sales of electricity to end users.
Combining those 2 facets of our research with the technology findings, we found that rather than continuing to implement centralized coal-based power plants in China, that we should provide more distributed plants and group of smaller gas-based plants for future areas.
Brennan. I'm a freshman here at WPI Environmental Studies major.
And I'm Emily Fournier, and I am a chemical engineering major in the environmental concentrations, and I'm also a freshman.
Right. Our project is from the Grand Challenges seminar. We did it freshman year at A and B term. And our project was on separating the greens from their lights and darks. So basically it was studying the WPI and this current laundry system and improvements they can make to make the laundry system more sustainable.
I'm Shara Bradley. I'm Bianca Castagna.
I'm Daniel Miller. And I'm Ryan Kimball. And this is the Wave Water Vapor Condenser. We set out to solve thirst across the world. We took regions of interest which both have high humidity and big need for water, and we try to design a device that can extract the water from the air and condense it for human consumption.
I'm Nick Alden.
I'm Shigen Chen.
It's actually mandated developing an sustainability report for WPI.
And it's the first sustainability report of WPI, and from now on, WPI knows it's past, it's present, and will declare for its future.
My name is James Hogan. I'm Pete Cacciatore. And we worked on developing a best practice manual for sustainable landscape architecture. The four of us went up to Edmonton, Alberta to work with Stantec, a multidisciplinary civil engineering company with about 150 offices across North America. We had 9 different sustainable landscape architecture topics that we compiled the potential benefits, risks, and various other considerations, costs, and we compiled them into a best practices manual. And then we posted this best practice manual on an internal server for the Stantec in order for use of engineers to determine whether or not these practices are suitable for the projects they are currently working on.
I'm Nick Catano. This is our project on the development and validation of the Watershed sustainability for the Reventazón River in Costa Rica. And what we went to do for our IT project was to evaluate the current health of the river and the watershed and try to improve it and create a proposal to UNESCO to gain funding and future assistance on constantly improving the watershed.
I'm Alex Slam. This is Lan and Zan. We did an IQP where we conducted a literature review, risk assessment, and set of environmental guidelines for 2 very important nanoparticles, nanosilver and carbon nanotubes. Nanosilver is currently the most commonly used nanoparticle. It's used in soft as an antibacterial. Nanotubes have a huge potential in electronics and in a lot of other fields. In our literature, we drew on the results of nearly 100 papers throughout the literature. We focused on a lot of in our risk assessment, we tried to evaluate them, and in our guidelines, we look at mitigation, future directions for research.
This risk assessment is pretty crude, but it combines the best knowledge we know in the field. It combines professional practices of having high and low scenarios, having safety factors and stuff. And the conclusion is that in a high risk scenario, there might be some risk for nanosilver, but in low risk scenarios, there's no risk. So the basic strategy is that we don't need to cut production or limit use, but we do need to use some risk mitigation technologies, such as structures that can trap nanosilver so that they don't leak, and also ligands that can bind nanosilver so that their bioavailability is reduced, stuff like that. For our guidelines here, basically first we encourage research and application of these strategies. Secondly, we think there needs to be more research into the behavior of nanosilver in biological bodies and also in the environment. So these are the points that was pointed out. And also, since nanosilver is an antibacterial agent, the government has the power to collect data from manufacturers, but they're not doing that now, so we suggest that they do that. And finally, manufacturers, companies should label their products as containing nanosilver, because consumers might want to know. Actually, many companies are already doing that now, but we hope to make it more popular.
I'm Owen Butler, and with Kelsey McMenemy, Ryan Lefebvre, and Megan Elwell, I did a project on urban planning and redevelopment in Montreal BC Park. This took place in Cape Town, South Africa, and we worked in an informal settlement, which is basically a shanty town. Most houses are made of sheet metal or plywood, 2x4s, nothing fancy, stuck together with whatever nails and wire they can find. And there we worked on urban planning for developing roads, sewer systems, and other basic necessities, as well as working with other teams on economy and food and many other aspects of life. Our main job was to come up with an overall plan for redevelopment, as well as mapping and GIS software for all of the teams that were at the project center.
Hello, my name is Jason Beliveau. This is Farzan Tariq. We're up here at Niachiko and Chaolian. And for the past 4 months, we've been doing a feasibility study regarding the photovoltaization of WPI's campus. Our research has yielded that there are about 600 square feet of available roof space to us on campus. And with that available roof space, we can build various photovoltaic arrays that will number in about a 426 kilowatt system size.
Can we all gather at this end?
With our various systems, we'd be able to produce about 500 kilowatt hours per year. And by producing that energy, our cells in a clean and green way will be reducing carbon emissions by about 400 tons per year, which is the equivalent of planting about 1,900 trees.